This is problem 41 from the photon. In problem 41, a 1.8 mega electron volt photon interacts with a hydrogen nucleus and creates an electron-positron pair. The electron and positron travel at 35 degrees from the initial direction of travel of the photon. Find the kinetic energy of the electron and positron, assuming the nucleus is at rest after the interaction. So, we're going to use conservation of energy. We have the photon initially. The photon creates an electron and a positron. So this is the energy, the kinetic energy plus the rest energy for the electron and the positron. And also, if we look at conservation of momentum, in the y direction, the photon's momentum was in the x direction to begin with. So in the y direction, we had 0 initially, and afterwards we have the positron, and the y component would be sine of 35 degrees. That's positive, and then we have the electron, which is going downward, so that's negative. This is the momentum of the electron times sine 35 degrees, which means that PC for the positron times sine of 35 degrees has to equal PC for the electron times sine of 35 degrees. We got a sine of 35 degrees on each side, which we can cancel out, which means the electron and the positron have to have the same momentum. But by our equation, E squared is equal to MC squared plus PC squared. If the momentum is the same for both, then since the rest energy is also the same for both, they must have the same energy. So the energy that you have initially splits evenly between the two. So our equation up here would be 1.8 is equal to twice either the energy of the electron or the energy of the positron. So the energy of the electron is equal to the energy of the positron, and that's half of the 1.8 mega electron volts, so that's 0.9 mega electron volts for the energy. We're supposed to find the kinetic energy, but since I now have the total energy, and I know the total energy is equal to the rest energy plus the kinetic energy, I have kinetic energy is equal to total energy of 0.9 mega electron volts minus the rest energy. This is an electron or a positron. They have the same rest energy, which is 0.511 mega electron volts. So the kinetic energy is 0.389 mega electron volts. That's our answer for part A. In part B, we're going to find the kinetic energy of the hydrogen nucleus needed to ensure momentum conservation. Would this amount of kinetic energy greatly affect the result in part A? So this was assuming the nucleus is at rest. Now we're going to see if we don't assume the nucleus is at rest, what energy it would need in order to ensure momentum conservation, and see if this would make a difference in our result for part A. So we already did conservation of momentum in the x direction. Now we're going to do conservation of momentum in the y direction. No, that's what we already did. We're going to do conservation of momentum in the x direction. So initially we have the photon moving in the x direction, and the momentum of the photon is the same as the energy of the photon, so that's 1.8 mega electron volts. Now afterwards, we have an electron and a positron and a nucleus all going in the x direction. So this is PC for the positron, but this is only the x component. So this is cosine of 35 degrees plus PC for the electron times cosine of 35 degrees plus PC for the nucleus. Now, these two, because we said up here their momentums are the same. This is going to be twice the momentum. Did we find the momentum up here? I don't think that we did. So we have to find what PC is times cosine of 35 degrees. So it's the same for both. And then once we find that, we can find the momentum for the nucleus. Okay, so for the electron and the positron, we had the total energy and we have the rest energy. So we can actually use this equation up here to find the momentum. If I take this and rearrange it, I get the total energy. The total energy was 0.9, so this is 0.9 squared, minus the rest energy, which is 0.511, and that gives me 0.741 mega electron volts. So I can take this, and I can put it in here. I'm going to take this whole equation, put it down here. This is 1.8 mega electron volts is equal to 2, since I have a proton, or since I have an electron and a positron. This is 2 times 0.741 mega electron volts times cosine of 35 degrees plus the momentum for the nucleus. So the momentum for the nucleus is equal to 1.8 mega electron volts minus this, which is 1.21 mega electron volts. So that gives me 0.586 mega electron volts for the momentum for the nucleus. But I'm actually trying to find the kinetic energy for the hydrogen nucleus. Well, I can find the total energy by doing En is equal to the square root of Pcn squared plus mc squared for n squared, which is using this equation up here. I need to know the rest energy for the hydrogen nucleus, so I can pull out my periodic table to find the mass in atomic mass units. That's 1.0079. Then I go to page 1 of the appendix, and 1 atomic mass unit is equal to 931.494 mega electron volts per c squared. But this is mass, and I want rest energy, so I'm multiplying by c squared, so I can just change that to 931.494 mega electron volts. Multiplying that by the 1.0079 that I had from the periodic table gives me for this 938.9 mega electron volts. And so now I have my momentum of 0.586, my rest energy of 938.9. That gives me the energy for the nucleus. I'm trying to find the kinetic energy, so rather than doing this, calculating this, I'm going to pull out the 938.9, and so this would be 1 over, this would be 0.586 squared divided by 938.9. So this is the same trick that we did 2 problems ago. So we're pulling this out, and then I can say energy total is equal to rest energy. So this is equal to mc squared plus Ke for the nucleus. So what I'm pulling out here is the rest energy. If I take this and use my approximation, so this is 1 plus something really small, so that's approximately equal to 938.9, and I take the power. Usually this is written the other way around, but it would be 1/2 times the really small thing, which is 0.586 divided by 938.9. This is still squared plus 1. So this times this gives me the rest energy, and the 938.9 times the 1/2 times this gives me the kinetic energy. So the kinetic energy is approximately equal to 1/2 of 0.586 squared divided by 938.9. And that gives me 183 electron volts, compared with what we had up here for the kinetic energy, which was 0.389. So compared to 0.389 mega electron volts, 183 electron volts is not significant. So this is the kinetic energy, and this is safe to ignore. That concludes problem 41.